Yeah, I think Liam covered some of the things that I was planning to talk about. So I decided instead we would just be inspired by Wen Fei and just discuss poetry. No. So actually, this is a slide I didn't have in the talk, and then I did put it in after seeing her little moment of poetry. So this is a slide I sometimes use in dark energy talks because it beautifully describes the sort of semi-sense of chaos in the dark energy community, where we're trying to figure out what's going on with dark energy by looking at different sides of the beast. Okay, the whole poem is not up there, and if you don't know it, you can go away and read it and understand that, of course, this is supposed to be about theology, the elephant that no one has seen. It doesn't quite apply the same to FRBs, because you're actually seeing something here, but my takeaway from having sat through this meeting and learned a fortune from all of you is that there are actually a fortune of things that you can do with FRBs, and there are a fortune of ways to possibly understand what the progenitor mechanism is behind them, and so we should be open to novel and new ideas. So to zoom out completely dramatically from the FRBs to what we think of as concordance, so you often hear about concordance cosmology, and the picture there is that we understand maybe 5% of the universe, the rest is just dark, and so we put the word dark in our grants and get lots of money. And the standard model is supposed to also have some kind of concordance. These are the particles. You know that you've succeeded when you've made it to the commercial point. And the Higgs boson should now be out the theoretical and into the non-theoretical, I guess, the real. And dark energy is so far-fetched in some sense that it hasn't even made it to the point of being worth commercializing. And so we put this up and we think, right, we're done with particle physics, we understand all the particles, but it's not true at all in the same sense that cosmology is not at all done. Okay, then we don't understand how neutrinos get mass, the tachyon shouldn't be there, I don't know what to say, and dark matter, I don't know, it wasn't me. And I would buy it though if I saw this in a store. And dark matter is also completely not well understood. And so zooming out even further, if I wanted to give you a full theory of everything, I would have to give you I would have to write down two theories. So the one is a theory of gravity, the other is a theory of matter and its non-gravitational interactions, okay? And then I need to give you two more things to fix my theory, which is a choice of geometry and a choice of topology that are usually forced on you by data. So these are the known knowns, right? I did my PhD in the Bush era, where that phrase caught more ire than it does today, thankfully. And so all of those four things give you what we see in modern cosmology today. You get the fact that the universe is expanding, and we look back and we see this relatively homogeneous temperature back to the early universe. So those are the known knowns. The known unknowns, I think the three big ones are dark matter, dark energy, and inflation. And there are sort of large gaping holes in what we think we know about cosmology and about the universe, but we don't refer to them that way. We still think of ourselves as moving towards concordance and everything working. And everything we know about them is from indirect detection. There's no direct detection of any of them. There's been a really large amount of money, time, and energy spent on direct detection of dark matter with zero outcome. And so this isn't the way that I came to think about FRBs, but you always tell the story in a different way. And so the more recently, I think we've hit what might be the crisis that completely breaks concordance, which is the H0 problem. So the fact that measures of the early universe and measures of the late universe give us different values of H0, the Hubble constant, or thinking of it a different way, looking on different scales, large scales versus small, you get a different value, tells you that something might possibly be really very wrong. There are also papers that are sort of undermine the case for dark energy. So I think, cosmology was certainly a field that was pure philosophy not that long ago. Then the last 10, I think since WMAP, we've been talking about precision cosmology, very excited. And I think now we're a field that's in crisis. So some possible solutions. The first is to relook at the data and how it's studied, etc. And that'll probably resolve the H0 problem. But I have zero chance of making any contribution to that, so I just leave it there for those who are already doing this, so it's somewhat useless to me. The other two approaches, which is if you know your history of astronomy, you all know about Urbain Le Verrier, right? The guy who discovered Neptune and almost discovered Vulcan. It's a lovely story that I don't have enough time for here, but basically you have two options when you don't understand your data. The one is there's new physics, okay, and the other is that you need a new theory of gravity. So the new physics was Neptune, and the new theory of gravity was general relativity that explained the precession of the perihelion of Mercury. There is no planet Vulcan between Mercury and the Sun. So these are things that I'm working on. So I have put up my students' names just in case you see them later. They're each doing sort of various different projects. So Rebecca's working on ways to explain the H-naught problem with new physics. And I have a student, Irvin, who's working on using gravitational waves, so using a strong gravity environment to constrain theories of gravity that we can then feed back into cosmology. The other is to look at different ways to probe cosmology. And this is really how I landed up sort of thinking about FRBs. And there we can say, well, what can you do with FRBs? How can you use them as some kind of standard something? Sirens, candles, what standard measures can you make? And Anthony Walters was my PhD student. He's now a postdoc, stuck in China as we speak. And Emma Platz is my current PhD student working on these sorts of things. So an example, I don't need to tell you any more about the lensing because covered it very, very well, but you could use, so an example to constrain large-scale features, right, is you could use strong lensing of FRBs to constrain H-naught and also the curvature, but you have to make these assumptions. For the former, you have to assume the universe is flat, which some people are very happy to do, but it's a prior that you're putting in. And for the latter, you have to assume lambda CDM, cold dark matter, and a cosmological constant. You could also test the cosmological principle, i.e. we don't live in a special place in the universe, and you can use FRBs to exclude some kind of large dipole anisotropy. You need very few to do that. If you want to exclude a very small dipole anisotropy, you need a lot of them. And again, you've assumed the prior of flat lambda CDM. I'm talking about a bunch of people's work here, so some of you are even in the audience. I apologize if I butcher it. Feel free to correct me. So there are implications at various different scales. So for the early universe, you can get the helium reionization signal. I think there's a paper from like a few days ago. But it assumes that we can see FRBs out to a redshift of 5. Someone said earlier a redshift of 50. I don't know how realistic that is. I just don't know. I know, but a redshift of 5 is also not trivial, right? The furthest seen is below 1, right? So all these, in any sort of progress that you're making in some kind of cosmology requires you to take a bunch of these assumptions. The implications for the late universe are possibly the most obviously interesting. The micro-lensing by machos was already covered, but you get this sort of slightly doubled peak view of your FRB. Again, a whole lot of assumptions have had to go in to make that work. And it's possible to probe the intergalactic medium. I think Brian talked about this the other day, but again, this assumes some kind of progenitor. There's no really model-independent way to do cosmology. You can break the optical depth degeneracy with the kinematic Sunyaev-Zeldovich effect. So there you've got the fact that photons from the CMB have a peculiar velocity relative to the CMB, and scattering off of those is going to give you some kind of, it changes the observations, and the optical depth is degenerate with that effect. And so all of our fantastic cosmology surveys are unable to break that degeneracy, but a huge number of FRBs will. Problem is, you need 10 to the 5 localized, which was ridiculous last year. Maybe it will be realistic in 5 years or in 2 years. I just don't know. So all of these things build in a whole lot of assumptions. There's more esoteric things, so constraining fundamental physics. Does the photon have mass? These are the kinds of questions that probably most of you are like, no, it doesn't, lady. Why are you talking about this? But we worry about these things. Until something is completely ruled out, it's entirely possible. And so you could constrain mass limits on the photon. Again, you need very accurate redshift information for your FRBs. And finally, if you find gravitational waves and FRBs at the same redshift, then you could create a better standard siren than gravitational waves alone, even if they're not associated with the same event. If you can pin them down to the same redshift, you can do great things and get better constraints on H-naught. So there's a bunch of really nice things you could possibly do with cosmology, and I think given that I'm in the future section, I think there's a lot more to think about still. We just have to be extremely careful about the priors and the assumptions that go in. And that's something that I generally worry about anyway. So the small contribution that I've made to this area with really my students, so Tony Walters did the Lions work here. If anything is wrong, that's Brian's fault, not mine. I'm kidding, you guys. Not okay. So what we wanted to do is see, could the dispersion measure as a function of redshift be used to constrain curvature? So dark energy was already done, the dark energy equation of state possibly being allowed to vary. But the question is, can you get better curvature constraints? And I'll show you in a moment why we even care. And the point is, all your cosmology comes in over there, right? All your cosmological parameters come in there. Usually omega k is set to 0. We assume it's very small because it appears to be relatively small, even though positive is a sort of slightly favored in the data. And so the question is, can you constrain the curvature, and can you allow for a varying equation of state at the same time? So you have different contributions coming from different components. One audience I don't have to explain the slide to. There's also a possibility of stuff coming from the halo of the host galaxy. And not surprisingly, probably it would be trivially obvious to the rest of you, but it was not to me as I entered, you're not going to do very well with just FRBs, right? You get these huge, slightly useless ellipses because FRBs are so recent and curvature is so small that you need to go very far back in redshift to do anything. But if you allow yourself to add all of your Planck priors, then you get slightly better constraints. And obviously in Omega baryon, because the dispersion measure is probing the electrons between us and the source, and so it's Omega baryon that you're really probing. If you wanted to allow for a non-flat lambda CDM, the Omega baryon versus the curvature, again, requires you to input a whole bunch of priors. So the obvious thing to do, to some, it took us a little while to get there, is to turn it around and say, well, if we treat the cosmology as precision, we input the cosmology as the priors, then you can constrain FIGM. And so you should be able to, if you get the right number, you should be able to resolve the missing baryon problem, which I think is an obvious and very good, and it's probably like, for many of you sitting in the audience, it's probably like watching a toddler figure out how to walk. The fact that a bunch of cosmologists came and figured out something that's likely very obvious to you. But yeah, so we figured out that you could do that. And then you might say, well, has someone made a bet with you if you could put the word multiverse in an FRB talk? And basically, no. It's just, I just include the slide to say that we do care about curvature. And you know, you can assume that it's zero, and people do assume that it's zero in most of cosmology work now. If you look at the Planck data, if you look at the Planck constraints on dark energy, it assumes zero curvature. And if you look at the constraints on curvature, it assumes a non-evolving dark energy, because there's a degeneracy between the two. And if there is some signature of curvature, it rules out entire chunks of inflationary possible histories and chunks of the multiverse. So very, very extreme theorists do think about these things, and it is kind of important. And this is one thing that we are doing actually with HIRAX, which is to use the 21 centimeter intensity mapping to put constraints and to break that degeneracy. So I'm almost out of time. So I'll just show you the numbers here. So HIRAX can do a lot better and allowing a varying equation of state of dark energy. Okay, so just a few words on HIRAX. I think you've probably heard a little bit. I think Mara had a little bit in her talk. So the ultimate goal is to have 1,024 6-meter dishes in a close-packed array. This is obviously an artist's rendition. That is the HIRAX, the closest living relative to the elephant genetically. And they live near the meerkats in the country, and HIRAX is going on the meerkat side. So it's a very well thought out name for the telescope. It's in the process of being built, so we've built the first sort of prototype array is built, and the original science goal, which is how I got sucked into it, is dark energy. It's to do intensity mapping with baryon acoustic oscillations, but it turns out that, at least from where I'm sitting now, the FRBs are possibly the more interesting science, and there's a huge amount of potential to be done there. It's very much complementary to CHIME with no snow. So there was a comment about RFI, and I don't know if you can see this, but in 2008, the South African government passed an act of parliament called the Astronomy Geographic Advantages Act, which keeps the Karoo radio quiet. So you are not allowed any possible source of radio interference there. People don't have cell phones at all. All the farmers, anyone who is there has like a satellite phone. It's totally, entirely protected. And so the RFI in this band that we're looking 400 to 800 is extremely low. Right? This is as close as you'll ever get to data from me. So it's a very, it's an amazing opportunity for HIRAX that we saw once the SKA was already going on that site, and that site has been protected. And so there's a huge amount that you can possibly do. Okay, so the main array will sit over here, and then the plan is to put outriggers not only all over the country, but in partner countries. And so we involve other African countries. So the plan currently is Botswana, Rwanda, possibly Kenya, and possibly Mauritius. I had to Google the distances. It's about 2,000 to 3,000 kilometers. So it's a decent distance that gives you sub-arc-second resolution in the end. And so it seems to me from where I sit that localization is like the most important thing. You're going to learn so much if you can localize your FRB. So instead of getting a vague sense of a galaxy, you get the exact point. And if you're going to do any cosmology, you absolutely have to you have to have your localizations. You have to know where they are. So just some final thoughts, which are my own personal musings from sort of being on the edge of the field for the last year or two and from sitting through the week. So the first is that I come from a particle physics background, which is that, Feynman said that if a particle can exist, it must. If a coupling can exist, it must. And the only way that it doesn't is if you rule it out. And so when you show different types of FRBs, when I'm seeing, the repeaters that appear to be periodic, those that don't, non-repeaters, to me it seems as though the way to look at it isn't that we've found this progenitor model that explains all these amazing features. It's rather that many things out there can make fast radio bursts. And if you don't see what you've predicted, you've ruled out some physics mechanism. So if we don't see Janna's black hole battery, from the neutron star black hole mergers, then that's telling us something, right? Something is constrained there. And that's the sort of approach that I sort of expect. So I expect to see tons of different kinds of FRB progenitors sort of surviving at the end. That's at least where I'm sitting from far out, and that we should use that to constrain other physics. And the example I have here is a cute paper that we wrote just looking at the event rates from cosmic strings. So cosmic strings, in principle, can give you this burst in the electromagnetic. Turns out it can be in the radio. And can you get the right event rates? The people who had originally looked at this stopped working on it because once the polarization was seen, the polarization is expected to be circular. Once they were seen to be linear, they assumed their theory was ruled out. But I think now that there's more data, we realize actually it's not as crisp as you might think. My next question that I think I might have asked a few of you over meals is how are they distributed across galaxies? So do you expect them to be spread like butter on toast, or are they sitting more towards the edges or towards the middle? Because I'm sure that tells you something. If they cluster in different types of galaxies in different ways, that must tell you something about the physics of them, right? So I think there's a whole lot to learn by just looking at patterns. And as a mathy person, it's really the patterns that I'm sort of desperate to see all of your data to see where the patterns are and what this will tell us about the progenitors and about cosmology. And then our catalog is up there. This was a project, really, Emma did a huge amount of work, and we had to sort of recruit Sriharsh to make sure that we didn't talk any astrophysics nonsense, because really, as you can tell, we're a group of total theorists. So my last slide, I think I'm already into the discussion session, is just to show you the beautiful university and city that I live and tell you that we're hiring 2 postdocs and we have funding for students. So if you have anyone who wants to go where it's warm and sunny, please check out the webpage.